Good morning, everyone, and good evening or good afternoon. Thank you for joining us for today's webinar. I'm Tricia Fitzpatrick, the Marketing Manager at Homer Energy by UL, and I will be your host today. We have a very full agenda for you as we explore the importance of mitigating risk over the life cycle of a mini-grid or distributed energy project. We're fortunate to have 4 expert speakers on this topic. Since Homer Energy was acquired by UL in December 2019, we now have access to expertise that covers many areas. Our presenters today are Peter Lilienthal, who is the founder of Homer Energy and now the Global Microgrid Lead for UL, Joseph Padbury, who is UL's Business Development Manager in Sub-Saharan Africa, James Trudeau, the Global Business Development Manager at UL, who is responsible for energy storage systems and e-mobility, and David Mincer, UL's Head of Microgrid Advisory Services. Marilyn Walker will be moderating the question and answer period, and Marilyn is also a founder of Homer Energy. In today's presentation, Joseph Padbury will share his expertise on the growth and need for microgrid and DER systems in Africa. Peter Lilienthal will present the importance of design and the role of solar and storage. James Trudeau will explore energy storage, the benefits and risks, and how to tie it together from a hardware perspective. And David Mincer will examine risk mitigation in terms of the bankability of a project. So now we'll get the presentation started, and I'll turn the mic over to Joseph Padbury.
Good afternoon, all. So I'm going to start with a brief introduction to UL. UL was founded in 1894. The founder of UL wrote the first standard for electricity going into the home. Since then, UL has advanced safety through science-based research globally. In 2012, UL acquired Devi, a German renewable energy consultancy, and a few years later bolstered the renewables division with the acquisition of AWS True Power and more recently Homer Energy. These acquisitions allow for the UL renewables team to provide technical advisory services in solar, wind, and energy storage systems throughout the life cycle of project development and operational phases. The combination of teams from Homer Energy, AWS, and UL has built a strong advisory team embedded with deep knowledge of how equipment performs in operation. UL has over 100 office locations globally, with over 500 team members in the renewables division. UL have advised over 90% of the wind industry's top project developers and plant owners, earning UL true global experience and market knowledge. Our topic today discusses how to optimize design and mitigate risks in mini-grids. But why mini-grids? There are an estimated 600 million people in sub-Saharan Africa without access to electricity. The United Nations Sustainable Development Goal is to ensure sustainable, affordable, reliable, and modern energy for all by 2030. It's often too costly to extend the grid to remote communities. With the rapid development of technology and reduction in prices of components, mini-grids are now a practical and viable solution. Mini-grids offer cost-effective, rapid deployment options for utilities and private developers for rural and isolated communities. However, in order for mini-grids to be safe and sustainable, meeting the needs of the end user as well as the funders, there needs to be real effort made in risk mitigation, from the initial concept design through to equipment selection. I'll now hand over to Peter Lilienthal, the founder of Homer Energy, who will discuss mini-grid design.
Well, thank you, Joseph, and thank you all for attending. I'm going to give just a tiny history about Homer first. We were started back at the National Renewable Energy Laboratory. Well, the software was originally designed back at NREL in the early 90s as a research tool. But I always felt that it had commercial potential, and it's gone through many iterations in the ensuing years. In 2009, we spun it off as Homer Energy with a license to Homer Energy. Created the company to commercialize and distribute and enhance the software. And in 2014, we came out with Homer Pro, which is really designed for the mini-grid market, the energy access market, especially in Africa. And then in 2018, we came out with HomeGrid for grid-connected projects, and we're in the process of creating a new product for front-of-the-meter larger projects. In the meantime, we've become a de facto standard around the world. We have over 250,000 people have used Homer, and over 120,000 really have opted into our network and get our monthly newsletters, etc. It's been used all over the world. Those dots on the map are places where projects have been modeled using Homer. That's over 75,000 projects and 3 million Homer files. So we have quite a database. So next slide, Tricia. So let me explain a little bit about what it is, although many of you probably already know, but at its heart, it's a simulation model that chronologically, step by step, whether it's hour by hour or minute by minute, steps through how a system would operate when charge batteries, discharge batteries, backup generation, load management issues, does that all chronologically, typically for 1 year, but you can go out to as many years as you want. To do this, you need inputs about things like interest rates, prices of equipment. The load profile is very important. We have generic load profiles that you can use if you don't have many measured data. You need the renewable resources, so we have databases for that. And since our merger or acquisition by UL, they're kind of a leader in renewable resource assessment. And you also have to say what kind of components you're looking at and what are you interested in. So Homer will simulate how a system operates, as I said, and it does that for dozens or hundreds of different systems and ranks them by total cost of ownership to find out what's best or what's the least cost solution. But you do see results for all of the solutions that it simulated. So that tells you what's best, but only for a particular scenario. And what's very striking about the energy access market is we're developing relatively small systems in places where they may not have had, they probably have not had power before. So there's a huge amount of uncertainty about things like the load profile, but even just what's the cost of getting something installed in a remote location. So we believe sensitivity analysis is really important for risk analysis and risk mitigation. So we've built that in as an integral part of Homer to do sensitivity analysis on any of the parameters where you may not know for sure what the right value should be. So you do sensitivity analysis on it. So that's sort of the structure of it. And then it reports out clearly, you know, how much did things cost? What was the cost of energy? How did it break out between capital and operating costs and replacement costs, et cetera? What's your IRR or return on investment? And how did everything perform? You can dig in and really see hour by hour how the system was going to operate. And we've come out with a new proposal writer, so it will produce a professional-looking proposal that a developer could take to a client to show them it's really designed for our customers to show their customers. So next slide, Tricia. So let's talk about what are the options for energy access. In the old days, you really only had two choices. If you could extend the grid, and the grid could handle the extra customers and power requirements, which is a big question. But grid extension is sort of the default. And if you were too remote, they'd put in a diesel generator. So that's the old approach. Diesel generators don't work at low loads very well, so that so those approaches typically didn't provide 24-hour power. The new approaches, now that solar and storage have become affordable, MiniGrids can provide 24-hour power, and talk more about that in a minute. The other approach that's really taken off are solar home systems, or standalone single individual solar systems, much simpler, typically not 24-hour power, but it's simple. And so it's good for small loads and small homes. Next slide, please. But first I want to just talk a little more broadly about the distributed generation landscape more broadly. So distributed generation is just, smaller systems that are where the power is produced where it's used. And so that can be, you can see in the middle picture there, that's a food distribution facility in New York State. So it's a big grid connected project. That's distributed generation also. Microgrids is a subset of that has this capability of running in an isolated from the main grid. So that's a lot of interest in the US, where we've had a lot of hurricanes and wildfires, and the grid has gone down for extended periods of time over a region. And so there's a lot of interest in microgrids in the US now. Even though they're grid connected, they need to be able to operate off grid. What we're going to focus on here, mini grids, always operate isolated. They're never grid connected. So these are subsets of each other as you work down the my list here. And so mini grids are what we're really focusing on here. Next slide, Tricia. So let's talk about how do you decide whether to extend the grid or to use a mini grid. If you're close enough to an existing grid and your load is large enough, then a grid extension might make sense. The other characteristic that you really want to think about is, well, will the existing grid handle new customers well? Because in many parts of the developing world, the existing grid is not that reliable. They're not serving their existing customers that well. If you want reliable 24-hour power, you probably have to do it yourself anyway. So those are the three parameters. And Homer has a capability that may not be really well known to calculate what we call the break-even grid extension distance. So it compares the cost of providing power to this load, whatever it is, a village, a mine, whatever it is, with either a hybrid system, which doesn't depend on distance, versus extending the grid. So those graphs on the right, the x-axis, may not be able to read it, but it's distance from the existing grid. The yellow line is the hybrid system, which obviously doesn't depend on it, and the blue line is the grid extension. And where they cross is what we call the break-even grid extension distance. So I've got two examples here for a very small water pumping system. If you're more than 460 meters, a half a kilometer from the existing grid, it's less expensive to put in solar and storage versus extending the grid. Now, if you're talking about a larger village, say the lower graph has a 62 kilowatt peak load, so that's a decent sized village. The break-even grid extension distance in that case is 6.5 kilometers. So it really does depend on the size of the load and the distance. And as I mentioned before, solar home systems are preferable for small homes. If all that a user needs is a few LED lights and maybe cell phone charging or maybe even a small fan, a solar home system is actually cheaper than a service drop. It almost doesn't matter how far you are from the grid if that's all the electricity you need. But as soon as you want a refrigerator or any more substantial load, that changes the picture. But solar home systems are nice and simple and they're easy, and if all you want is very small amounts of power, they're absolutely the right way to go. But if you want productive uses, which often involve motors, whether it's a sewing machine or an air compressor or a grain grinder or power tools, mini grids can give you 24-hour power. They can give you AC power. You can have a backup generator, so you can have as much power as you want occasionally. So that's much more effective for larger loads and productive uses. And so they've talked about what's become very popular now is what's called an ABC model, where you find an anchor client who's creditworthy, et cetera, and that is the anchor for the mini grid, both financially and from a load perspective and a management perspective, et cetera. But then you also can supply local businesses in the town, some of these small commercial operations that I just described. And finally, the consumer these villages may be satisfied with less than 100% reliable power in exchange for a lower price. So there's a lot of discussion about this what they call the ABC model as a way to develop mini grids. Next slide, please. So what we focus on at Homer Energy and the Homer software is all about designing these systems, and they have to be hybrid, typically, almost always, basically, have to be hybrid systems because solar doesn't stand on its own. It needs at least storage or a backup generator. If you have a good wind resource, that's great. If you have a hydro resource, Homer can look at all those things. But solar and storage with a backup generator is sort of the typical. But how big should the solar array be? How big should the battery bank be? How much do you need a backup generator? And if so, how much are you going to use it? That all depends on, there's all these trade-offs between these different design decisions. So yeah, you add more solar and storage, you need less fuel. But what does that relationship really look like? That's a great output of the Homer software. Also, when you have a hybrid system like this, in the daytime, the power is basically free. I mean, you probably have excess power in the middle of the daytime. But then if you have to turn on the backup generator, now the power is quite expensive. So there's some tariff considerations that are important there. Another design consideration is how much reliability do you need? So what's nice about a mini grid, a hybrid system, with a backup generator, you can provide 100% reliable power. And of course, the mining operations really care about that, but everybody likes reliable power. But what's the cost of that reliability? So that's a question that for Homer to answer. And in many of the smaller systems, they may decide, it's not worth the extra cost. But you can't figure that out unless you do the analysis. And that tends to be more true for smaller systems. So there's lots of choices, and often you have to operate with incomplete data. And that's why sensitivity analysis is so important. So let me talk about diesels for a minute here. For the longest time, that was the default way to provide power in remote areas. But that has completely changed. Diesel alone is no longer suitable for prime power. I can't say that more emphatically. Solar and batteries now provide less expensive power than diesels, and that's almost universally true. They are more complex, so that's why the design is really important, and people need to get familiar with them. But it is absolutely less expensive to provide power with the solar plus storage than with a prime power diesel and with a diesel by itself. On the other hand, diesels are ideal for backup power. It's an interesting comparison here where they're very different. Diesels have very low capital costs but high operating costs, and solar and batteries have very high capital costs but very low operating costs. So they complement each other very well. So diesel is great for backup power because it doesn't need to be used very frequently, and even using it infrequently like that greatly reduces the size of the solar and batteries, so greatly reduces your capital costs for a little bit of a trade-off on operating costs. So that's often makes a lot of sense, but you need some analysis to figure out those trade-offs. So that leaves, next slide, please. So that leaves, because the solar and storage, all of the costs are upfront. So financing is really the key to making this happen. They clearly have lower costs, but because it's all capital costs, it needs to be financed. How do you get the financing? David's going to talk about that at the end of the seminar, so don't stay around. But what finance people really care about is risk. That's sort of the theme for this webinar. And I'm going to pass it off to James Trudeau now, who's going to be talking about batteries, which are the and risks associated with these systems. And batteries are sort of the key, I think, in many ways. So take it away, James.
Thank you, Peter. Good morning, good afternoon, good evening to everybody. I'm James Trudeau, and I'm going to talk about energy storage and how you implement it, and what do you need to think about as you're doing it. Not so much from a highly technical point of view, but more from a project management point of view. And UL stands ready. Obviously, communicate with Joseph on this, but we have thousands of experts around the world. We're glad to help you with some of the technical details that you'll be considering as you look at mini grids, energy storage, solar, etc. But on energy storage, what is it? Well, the picture you see on the screen, if you're being able to do that, on the upper right, I've got a small energy storage system that would be suitable for a home or a small business. That can also be as big as large containers, like you see in the bottom right. That can be typically a 2 to 4 megawatt system right there. Now, energy can be stored electrically, chemically. It can be stored mechanically. But right now, the reality of the world is that lithium-ion batteries are over 95% of the energy storage market. But many other technologies, many other battery chemistries are being developed and worked on. Energy storage can serve loads ranging from, again, small homes to big utility projects. Now, just as developers and users and understand that the definition of energy storage has been changed by international fire codes like NFPA 855 and the IFC 2021. And basically, they've redefined energy storage to be pretty much any box of lithium batteries. It doesn't matter what it's used for. Storing energy off a mini grid, UPS systems, telecommunications, but anything over 20 kilowatt hours in size, that's about the size of a small mini fridge. So it doesn't take very much. Next slide, please. Now, there are great benefits that come with energy storage. Peter talked about some of those, but it really enables a much wider use of renewable energy. That can be solar, wind. It reduces the variability of those resources, which makes them much more grid friendly. And that's important for a lot of grids that aren't real strong electric grids. And again, it improves, if it's just used on the grid itself, it can improve stability of voltage and frequency. And by using it in a mini or a microgrid, it can be, enables a much broader use of these. I can now tie those resources like solar and serve people and store that energy. I get an excess of it during the day, but now I can use that in the evening, reducing the runtime of secondary sources like the diesel, as Peter mentioned. It can, depending upon how you're being served, it can provide much more reliability for end users. And if you are truly off the grid, where you're running diesel, classic examples would be small islands or very remote areas. A typical price of a kilowatt hour of energy provided by a diesel is around 45 cents US. Using solar and storage, that comes down to around 15 cents a kilowatt hour. And that price is dropping as energy storage and solar is becoming more common. But you see, that's 1/3 the cost. Now, as Peter mentioned, it has more capital cost up front, but much lower operating costs and lower user costs at the end. And the combination of solar and storage reduces not only air pollution, but ground pollution as well, and reduces the ongoing operation and maintenance costs. Next slide. Next slide. There we go. But as you had great benefits, you have great risks. You're storing a lot of energy in a very small area, and the majority of the time it stays in there just fine, but occasionally it wants to get out. We, for example, have had 28 major energy storage system fires in South Korea alone in just the last 2 years. I'm talking all incidents in excess of $1 million US. Next slide. We recently had an incident in America where a utility Can you give me the next slide on that, please? We had a utility operation in Arizona, near not far from Phoenix, basically explode. That building should normally be very square, but it's sort of poofed out, as you can see. As this thing started failing, it was producing a white gas, and they couldn't figure out what it was. The fire captain was standing approximately 1 meter in front of that door you see right under the APS sign. When the system exploded, he was thrown 25 meters through that chain link fence before he stopped. 4 firefighters were all seriously hospitalized. It was a mess. So things can happen with energy storage. So how do I get the benefits and avoid as much of the risks as I can? Well, let's understand the risks fully. The next slide, I want to show you how much energy is in energy storage batteries. That little green box that you see there, that's 25 small lithium-ion batteries. You could hold that in your hand. And we forced them to what we call an overcharge condition. And when a lithium-ion battery burns, it burns at around 1500 degrees Celsius. Understand how hot that is. Steel loses its strength at 600 degrees Celsius. So there's a tremendous amount of energy that's trying to get out of these cells. Next slide, please. Let's understand what it takes. Think of that module that is down to the lower right there. Let's do some math. A single one of those cells that you just saw, it has about 10 watt hours of energy. There's the 25 cells that you saw only had around 250 watt hours. A typical module that goes into this container, and that's just one module, has about 5,000. There's about 10 modules per rack. There's typically between 15 and 20 racks per container. Bottom line is a typical 2 megawatt container, like you see here in the photograph, has over 3,000 times more energy than what you saw in that fire example. Next slide, please. How do we handle this? We handle it from UL's perspective with a 3-layer safety approach. And this will vary a little bit about what codes and standards you use will vary a little bit where you are geographically, but the concept remains the same. Number one, we have installation codes. This is how you install equipment. Examples here would be the National Electric Code or the NFPA, that's a National Fire Protection Agency 855 standard for how you install energy storage systems, or the new International Fire Code, either the existing 2018 or the new 2021 code. Both specify specific standards of how you handle energy storage systems. Now, that's how you install it. Then you have the equipment itself. There are some IEC standards for this. The more comprehensive standard is the UL standard. That's first 1973. That applies to the actual batteries themselves. But UL 9540 is an overall system specification. And we don't care if you're using lithium batteries or whatever you're using to store the energy. It's technology agnostic. We don't care. But it describes how to safely have a system where all the pieces and parts talk to each other correctly. We think that many of the fires in South Korea were caused by, if you can imagine, 10 components put together to make an energy storage system. If all 10 don't talk together, I can get what we call a functional safety failure. UL 9540 addresses that to keep that system safe. But once you have to plan. You have to plan for a worst case scenario. That's just good business and good risk management. So we take those systems and we deliberately make them fail. We remove the safety issues. We, again, deliberately make them fail to find out what's going to happen if they do, and then plan around that. That means I now have my worst case scenario identified, proper engineering applied to it, and that's what the UL 9540A standard does. It looks for those mitigations. Next slide. So this whole discussion about energy storage really is all about risk management. And we believe that the use of good installation codes combined with good equipment standards, coupled with system testing and experienced independent project oversight. You need to have people who have done this before, looking over your shoulder, helping you manage your risk. That combination is the most effective way to manage the risk profile of any battery energy storage system. And that covers the financial risks, the operational and performance risks, safety risk, and environmental risks. But all projects live and die by economics. That's why the financial and operational risks are so important. And to cover that a little more thoroughly, David is going to take the ball and run with it. David?
Right. Thanks, Peter. And James, I'm so glad you pointed out the risk elements in making sure the critical equipment, be it a battery or any of the other components for that matter, is tested and validated and performing as stated, and that they're safe to use in their intended applications. This is just so important to get right. My name is David, and I head the Microgrid Advisory Group, where most of my time and efforts are spent working with developers, IPPs, and financiers to help make sure that their projects, your projects, are economically viable. The situation is that the applications are complicated. The systems are complex. They're hybrid based as a rule, and the lenders need projects fully de-risked, or as de-risked as anybody possibly could manage before they make an investment. And as Peter noted, Homer provides the analysis backbone not only because of the many degrees of freedom available to design the system, but because the same approach is key to de-risking and then validating that this all has a well thought out mitigation plan for the financiers to support. Definitely, deep techno-economic analysis and tools are required. And thus far, my 14 years in this sector, Homer's been the only tool that financiers have been found to be bankable. So one of the recommendations when working on a project is begin designing the system with such a platform and as early as you possibly can. Next slide, please. Sure. Once the application and the project goals are understood, it's time to design a system with these major system components and the functions that they need to support. As Peter noted, Homer also has a rich library of manufacturers' components so that you don't have to search too hard to set up the design. Plus, it has a number of sample designs to get started. But what's especially important to financing is the ability to run that sensitivity analysis on just about everything, and then run what if scenarios. What if the PPA rates change? What if the energy consumption and loads change? What if the cost of diesel rises or falls? What about operations and maintenance expenses? And then what if wear out on the energy storage platform is faster than expected or slower than expected? Perhaps there are other services that can be included in the system if that's the case. What if degradation profiles are different? Next slide, please. Once the sensitivities and risks are identified, organize them. Understand the impacts. Break them down into those you need to avoid because the probability and the impacts are high. Transfer those to a third party if you can. Reduce, and then hopefully what you're left with is a number of risk-oriented elements that you're going to have to tolerate, that you're going to have to live with, but at least the probability and the impacts are low. From a financier's perspective, they might not need you to have to run every possible permutation, but they are going to ask you to harmonize all of these risk elements throughout the project lifecycle. And one of the best tools to use is this classic risk matrix. What's the likelihood of it occurring? What's the impact? What are we going to do about it? What are we going to avoid? Hopefully we are able to avoid the ones with high probability and high impacts. Can we transfer them to another party? Insurance companies are prominent in this space in these regards. Certainly try to reduce. Next slide, please. So we have limited time together this afternoon, but I did want to share one view of Homer and how we use it to manage risks. For example, here's a situation with a MiniGrid project, including wind, diesel, solar, and storage. In the level 1 or avoidance category, situations we want to avoid high impact issues due to price variability of diesel. And this could be directly related to the host's ability to generate profit and then pay off that loan. One way to do this is run sensitivity analysis on the cost of diesel and the price variability. And perhaps the cost of solar and or energy storage is unclear, and you need to run what if scenarios for the same reason and to avoid unnecessary surprises in the level 2 category. Let's say the solar and wind are unpredictable. It's intermittent. The locations in cloudy areas, and we want an insurance company to absorb that risk. There are insurance policies in the marketplace that will do so, and Homer lets you run that analysis to determine the exposure. Extended warranties on key components, that's another form of risk transfer. There are other vehicles as well. In the reduction category, perhaps we find out that maintaining the equipment and ongoing operations is a concern. You can see that contribution of the OpEx, and you can see that by component. Again, what remains are things that we're going to have to tolerate. They're usually environmental. At some level, we hope so. Perhaps it's force majeure. There's a theft related. These are things that we're just going to have to absorb for ourselves. The situation is that systems are complex. With bankable tools to alleviate the stress in de-risking, and Homer is one of the tools that I've used for years, and one that financiers have used as well, for sure. I'd be remiss if I didn't reinforce some best practices. Use Tier 1 components, build a proper design, use quality standards, capture comprehensive warranties and customer service. Make sure that the products and the services have a proper foundation. Use reliable contractors with knowledge and operational experience of your particular project in your particular location if you can. Ask your construction firm if they have bonding. Will they carry performance guarantees? Do the manufacturers have warranty insurance? Compare similar distributed grid and mini grid projects and the customers that use them. Thanks again for sharing some time together and listening in on how one could de-risk projects. That's all the prepared material I had, so let me pass the mic over to Joseph for some final thoughts. Thank you so much.
Great, thank you, David. So as we learned, there's an acute requirement for electricity across Africa. Mini-grids and distributed energy systems present an exciting opportunity to fulfill unmet electrical needs in Africa. However, these projects need to be safe and sustainable. In order for a project to be safe, sustainable, and bankable from a technical perspective, we learned today that 3 key items should be considered. Project design should meet the needs of the user as well as the needs of the funder. Equipment selection is crucial for a project to have both longevity and to be safe. And finally, a project developer must be able to demonstrate that project risks have been identified and mitigated. Please feel free to ask questions to the panelists or just drop us a line if you want. At this point, I'll hand over to Tricia. Thank you, Tricia.
Thank you so much, Joseph, and thank you all for a really excellent presentation. Before we go to questions, and there are a lot of questions coming in, I do want to address one question that often comes up, which is how do I get started? There's several ways you can utilize UL's expertise. You can use Homer software to model your mini-grid and find the least cost solution. And you can download our Homer Pro software for a free trial at homerenergy.com/try-pro. If you have already had a free trial, you can renew your trial to get more experience. If you want to dive deeper into the program, we do offer premium support and online training. Or if you would like help with your modeling project, we do offer help as well. You can contact support@homerenergy.com. and our team can do the modeling work for you. Or if you would like UL's help with the full scope of your project, then you can reach out to Joseph to learn more about UL's advisory services. So now we'll go ahead and go to questions. Marilyn has been collecting questions for us. Marilyn, what do you have for us?
Thanks, Tricia. Lots of questions. And I won't get to them all, just so you know. So back to what Tricia was just saying on the last slide. If you do not get your question answered, please reach out to support@homerenergy.com. And there are lots and lots of things available to you on the web and on our website. So we won't get to all the questions here, especially all the questions about how Homer does specific things, but I'm gonna try to talk a little more generally. And I'd also like to ask all of the speakers to please go ahead and unmute themselves so that we can go ahead and get through this. So I had a question for James regarding battery end-of-life storage for lead-acid batteries in rural areas and environmental damage. And if you have any thoughts or insights on that, how to deal with that in terms of the risk.
No, the risk is there. Obviously, lead and a lead-acid battery is sulfuric acid and lead, neither of which you want in your local water supply. So recycling, and the good news about lead-acid batteries, they are the most recycled product in the world. So number one, find somebody locally who can recycle it for you. That is definitely the way to go. That's one of the reasons we recommend strongly avoiding lead-acid batteries in energy storage situations. One, they have a limited lifespan. They can only take about 500 full depth of discharge cycles before they fail. That is not the case with lithium-ion. Lithium-ion can oftentimes do thousands and thousands of cycles, and it doesn't have the environmental impact. It's not made of lead and acid. So my first advice is, if at all possible, avoid it. Number two, please recycle.
Thank you. Joseph, there's a question here about in Africa in general and in other areas of the world too. You know, how do you think about energy efficiency and grid optimization versus building mini grids or microgrids? Because it seems like there's a lot that could be done with the grid.
Yeah, so that's not necessarily my strength. I'd probably rely on David to answer that question. So maybe if we can pass over to David, is that all right?
Sure. David. Grid optimization and energy efficiency versus mini grids.
Well, I can jump in. This is Peter.
Yeah.
Energy efficiency is always the least cost solution. I mean, almost always, but it should always be evaluated. And that used to be even more true for mini grids, just because the solar and storage was expensive, but it's less expensive now. But that doesn't diminish the value of energy efficiency. Not sure I understood the question exactly. Could you repeat it?
Well, it was rather, I'm interpreting it a little bit, but they were speaking about making a decision, you know, about putting resources into energy efficiency and grid optimization in areas where there's a poor grid, and making financial investments there versus mini grids was my interpretation of it, and how to make those decisions.
Well, it's two different problems you're trying to solve. There is a problem with the existing grids in many developing countries have very poor power quality, and improving the energy efficiency within that grid would help that problem. But that's a different problem than the energy access problem. They're related in that I think it's just foolish for utility companies that do have a power quality problem and a reliability problem to be spending capital extending the grid when they should be expending that capital fixing what they already have, and let the mini grids do the remote areas. So maybe that's what that question was getting at, is that I strongly believe the existing utility companies that have grids already should be focusing on making those things work really well, as opposed to extending them. That's a very important point, I think.
Okay. I don't know if David is. David, are you there? Okay. I think David's having some sound problems. So Peter, I'll give this one to you. How are future component replacement costs financed in Homer or in actual projects?
Well, that's actually two different questions. In the real world, it is a challenge, especially for grant funded projects, because you'll get a grant for building the project, but historically a problem has been they didn't account for, well, what are we going to do when we need to replace the batteries? And batteries is the main issue really there. And as James pointed out, if lithium batteries don't need to be replaced nearly as often, so that helps a lot. And a privately financed and a privately owned and managed mini grid is much more likely to take this into consideration, where they have to set aside money for the replacement costs, or find a new source of financing for that. And it's a hassle, admittedly, but it's essential to have a sustainable system.
Thank you.
So that's in the real world. In Homer, excuse me, I forgot. You asked how do we do it in Homer. In Homer, what we do is we want to avoid an issue where if somebody sets the project life to be 25 years, let's say, and a major component gets replaced in 20 years, and you've got an almost new component there at the end of the project life, we don't want that to create oddities in the financial analysis. So we assume that components get replaced when they wear out, and they get financed by in the same way. We're assuming that each component, this isn't actually how it works in the real world, I know, but it's a way to get consistent analysis, consistent results. We assume that each component is financed with the term equal to its lifetime, so it can be replaced, and the replacement doesn't affect the cost calculations. So it probably deserves a little more explanation than that, but I bet there's other questions we should get to as well.
Yeah, no, that was a good answer. And actually, I want to address a few questions coming in. That one is, should I use Homer Pro or Homer Grid for these microgrid, mini grid analyses? Homer Pro is the right tool for this. Homer Grid is specifically for grid connected systems where you're mostly looking at reduction in your utility costs through adding your solar storage, maybe even backup generators. So for these mini grids, it's Homer Pro. The other question coming in, I'm getting some questions from component manufacturers who want to get their equipment into Homer. And if you have a component that should go in Homer and you are selling this component now, please reach out to support@homerenergy.com and they can help you get that into the Homer library. Okay, back to more of the questions that for our panelists. How does Homer manage changing loads over time? You know, so you often might have a project in a village or community, and you estimate the load, and it's going to change in 5 years.
Yeah, so we have a multi-year module that allows you to where Homer will do its analysis over as many years into the future as you ask it to, so up 20 years, whatever. And you can set load growth. You can either set it as a constant percentage, or you can actually create a trajectory year by year of how, because if you think, oh, it'll take 5 years before it really kicks off, or it's going to be really strong in the beginning and then taper off, you can create whatever trajectory you want of load growth. And with the multi-year module, you can do that with prices of components as well. We also have two. This is a little more complicated. Hopefully, I can explain it, but it's not that bad. We have two loads. Primary load 1 and primary load 2, and they can have different shapes. And you can do a sensitivity analysis on them in such a way that it changes the aggregate shape, and you can see what impact it has if, for example, daytime commercial load grows faster than the evening residential load, or some new load kicks in the future, or you want to do a real efficiency incentive on one type of load that wouldn't apply to other parts of the load. So you can get kind of creative by thinking about these two separate loads and how they could change independently of each other. The multi-year module is the simple answer to your question. Yeah.
All right. Thank you. Let's see, I'm trying to read and do this. Lots and lots of questions about what Homer does. And I really would like to get some questions for, and I do want to say, like, that is a deep topic. Well, actually, I want to address one question that's coming in about getting demonstrations of Homer. With the free trial, if you are signed up for a free trial and you are with a government or an organization that actually builds systems, please reach out to your sales rep or to sales@homerenergy.com and how to get signed up for a free trial. And we can actually then address your specific questions. And if it's a more general question on what Homer does, Support@Homer Energy question is there to help you.
And we have a 21-day, excuse me, Marilyn, but the reason we have a 21-day free trial is maybe the easiest way to answer that question is just to download it and click around, and it's got an extensive help file. So just download the trial version, and you probably can answer most of the questions for yourself, probably, hopefully.
Yes. Okay, I'm not sure what all these questions. Comment. That's a comment. Sorry. Okay, I'll just throw these out there at this point. They're coming in so fast, and maybe do one or two more, and then again, I apologize, we can't get to them all. I would like to get back to our panelists really quick and see if they have questions they really wish someone had asked. You consider low load diesel technology to?
So you can create your own components. The low load and so yes, the way you would model that is to have the efficiency not drop off as fast. You change the fuel curve, so Homer lets you create whatever fuel curve you want, and it has a minimum load constraint that you would reduce. Low load diesel technology is actually kind of promising technology. Might be a little late, but maybe not. And Homer can handle it. You have to create your own generator, but that's easy to do in the library. Just copy an existing component and change the parameters.
Great, thank you. Yes, so many great questions, and I really do wish we could answer them all in real time, and we just can't. I do want to go through. I don't think David's got sound. If he does, I'd like to ask him to speak up. So, James, are there any last comments that you wanted to make before we end this?
No, there's a lot of funding for energy storage projects coming. I know that the World Bank, for example, has a large energy storage program. So I encourage people to look at that. There are various funding sources as well. Energy storage is viewed as a very, very effective environmental solution to pollution, and therefore it's being funded along with microgrids, quite honestly, by a number of governmental organizations. So I would encourage people, if you're thinking about this, you'll find a fairly warm reception out in the people who are doing the funding.
Great, thank you. Great comment. And Joseph, I want to thank you for making this webinar happen by really reaching out to us. And Homer is new in UL, and Joseph is there in Sub-Saharan Africa, and reached out and said, let's work together to get this message out. Is there any final things you want to say before we end today?
Yeah, I think as a team, we're most interested in having sustainable, safe solutions developed and built in Africa. You know, it's littered with a number of failed projects, and what we want to see is safe and sustainable projects. So if you have questions about your project, about what technology to use, how to design, feel free to drop us a line. And you know, it really is our mantra that we want to help. We want to make sure that those projects are safe. So
Right.
yeah, drop us a line and we'll get involved.
Great, that's great. Yes, we've been wanting. This is wonderful for Homer, working with UL and having this international reach and people locally. So we're really excited about the possibilities here. Peter, any final goodbyes from you?
No. Let me just reinforce what I said before about about download the trial version and check it out. I'm looking at all these questions, and so many of them I think could be answered just by looking at the software. So and I want to reinforce your point about, you know, we've always had a lot of users in Africa, but we haven't been able to support them as well as we'd like because we're in Colorado in the US. But now we have a South African office and a large Barcelona office, and in India and Singapore. So we can support users all over the world better, especially the ones in Africa. So I'm tickled pink to be working with Joseph now, and hopefully, I'm assuming most of the listeners on this call are in Africa, and they should take advantage of Joseph and our African office.
Great, thank you. And I'll make one tiny comment and then I'll turn it over to Tricia. We did get a question saying, can we use Homer in other areas of the world? Yes, absolutely. That it's been used all over the world, and there it is agnostic as far as which site. Okay, Tricia, thank you all.
Thank you so much, Marilyn, and thank you to our audience who has really put forward some great questions. We are really out of time. I will quickly mention that we do have the 8th Annual Homer International Microgrid Conference coming October 12th through 16th. It is free to attend, dynamic speakers, full agenda is online, registration is open, so please take advantage of that. And I want to thank you again for attending today's webinar. If you did not get your questions answered, you can send it through to your sales rep or our support desk, and we will respond. Reach out to Joseph and watch for an email in a few days with a recording of this webinar. We do hope to see you at the conference. Thank you, everybody.